Okay, so let's try the next one. All right, so here's a classic case. Now I forgot my double arrow because there's no strong acid or strong base here. These are going to be equilibrium, so this double arrow is in effect, so both are going. So what we want to do here is figure out all the acids and bases on both sides and the conjugate pairs. Definite skill that you need, not very difficult. I'll show you in a second, so try that for size now. Again, best way to do this is see what it becomes when you go from left to right. That gives you a clue if it, what? Donated or accepted. This is in the Bronsted Lowry definition. And honestly, if you find one, the others have to follow. For instance, I'm looking at H2PO4 -1. Notice the -1's important. Its conjugate pair, same chemical, just plus or minus an H, is HPO4 -2. Now, why -2? It lost a positive, right. So this guy must have lost something. So it must be the one that donated the proton. And donating a proton is under the Bronsted Lowry definition of an acid. Okay, this one must have accepted. That's a base. Wait a minute. If this is the conjugate acid, this must be the conjugate base. If this is the base, it's conjugate acid. Because party people, acid, conjugate base, has to work this way. After you donate, you have what? One less, which means you are able to act as a base now. That will do what? Reform the acid. That's how it works. If you're getting lost, pick this guy. H2CO3 in the future becomes HCO3 -1. How did that happen? It donated a proton. This is pretty simple stuff. Okay? Hopefully, I'm not going too fast. Okay? Now, there's more to this. We're going to pick it up on the next sheet. Okay? But let's jump now to the best and most encompassing definition. So I'm going to draw a diagram here. Here's the Arrhenius definition. It's a small circle to show that it covered a small amount of acids and bases. It was the simplest definition because it was the first. It didn't know that other things were acid and bases yet. So to be an acid and base under Arrhenius definition, hey, you delivered an H plus into solution, you're responsible for the H plus in solution, and you're responsible for the hydroxide, that was negative ion in solution. But that didn't cover all things. We noticed that there was something called ammonia, and there's others, that were outside that definition. And so the next definition that covered that chemical and others was the Bronsted Lowry definition that we just covered. And now we're going to change that definition from delivering H plus and a hydroxide to just simply who is a proton donator, who's a proton acceptor. And it will cover more chemicals because, again, NH3 doesn't have a hydroxide in it, so you wouldn't say that is a deliverer directly of hydroxides. So it's not an Arrhenius base. But as we can see, by it accepting a proton from water, as someone said, you are indirectly producing the hydroxides that increase the pH. Okay, well, the Lewis definition, the Lewis definition is the best definition, and it's the most encompassing, meaning it covers all the other definitions. So whatever is an Arrhenius acid or a Bronsted Lowry acid, is also a what? A Lewis acid. Okay? Meaning that it covers all the acids and bases, including the one in this example given to you, which is CO2. I'll show you in a second. So here's CO2 that doesn't fall under the Bronsted Lowry definition. Why? If we look up here, we see our CO2. Now I know they say or, but CO2 by itself is an acid. If I bubble CO2 into a solution, the pH drops. Did anyone realize the solution I had up here, the pH was dropping? Because
you're spinning it.
I was spinning it, but I was also what? Delivering more water in contact with more what? CO2.
So breathing just makes it lower.
Right. Pure water that goes through an atmosphere where there's no acid rain. There's no particulates like sulfates or nitrates that are making acid rain. Acid rain, by the way, is nitric acid and sulfuric acid, mostly because of the burning of coal and of gasoline or an internal combustion engine that creates the NO2s. That creates the particulates that can react with the water to make nitric or sulfuric acid. That's acid rain. We'll talk more about that another day. But pure water that goes through our atmosphere has to go through CO2. Even though there's only like 300 parts per million of CO2 in our atmosphere, that's enough for rainwater to have a pH of about 5.5. Yes?
Wait, why is the NH3 with the acids? Or not just like C?
Oh, the NH3 is under the Bronsted Lowry definition of acid and base. The Bronsted Lowry definition falls right here. It's outside of the Arrhenius because NH3, as we just said, isn't a Arrhenius base because it doesn't have a hydroxide in it.
Isn't this for like Lewis acids?
For Lewis definition of acid and bases. Okay? So in terms of the Lewis Bronsted Lowry base definition, NH3 fits it, but doesn't fit, but it's not an Arrhenius base. Okay? But it is a Lewis base. CO2 is acidic. It cannot be a Bronsted Lowry what? Acid. Because it doesn't have any H's to what? Donate. So how do we explain it? Well, I explain it through something called a mechanism. For those that go to college and study organic chemistry, most all of you, if you go to the medical field, will see these mechanisms. This is an important mechanism because CO2 in our environment, it makes our what? Oceans acidic. You heard about it. As CO2 goes up because of greenhouse effect or producing more CO2 by us burning more fossil fuels, our oceans get more acidic. If their pH drops, okay, they're going to start dissolving something called calcium carbonates, okay, which is seashells or marine animals. And also just dropping the acidity will make what? The proteins that have R groups in them. Some of these R groups in the amino acids are bases and acids themselves, and they'll react with that, and they will no longer attract to each other, and this shape of the proteins, which are doing something organically, metabolically, will be misshapen and denatured by too many H pluses. So all of this matters. So, how does CO2 make our oceans acidic? How does CO2 bubble? Why did our pH drop? Well, CO2 has a electron dot diagram. It looks like this. Carbon has 4 valence electrons. You guys have all done this, everybody. Oxygen has 6. 2 there. You all have done this one. Okay? Now, this is appropriate. Now, when you think about it, when you learn this, carbon feels like now it has 8. Okay? Oxygen feels like it has 8, and carbon and oxygen are both what? Wrote 2 elements. They're both going to fill their second shell, which is a stability issue. So we predict correctly by putting dots on a piece of paper, okay, that this has a double bond on both sides. In fact, you could draw it this way. Here's carbon, double bonded to an O, and then 2 lone pairs, and double bonded to O with 2 lone pairs. Now, in truth, I'm going to redraw this a little bit differently. Carbon, oxygen, who's going to pull electrons more? Oxygen. So it's going to take these 2 and put it closer to. This is a more representative one. So you're going to put these 2 pairs closer to the oxygen. They're not shared equally. Most electron density is on the what? Oxygen side. This is how you really look at it. Now, when you do that, party people, what's happening is we're pulling the electrons. I love these. So the electrons are being pulled away from the carbon, correctly?
Yes.
Yeah.
And when you do that, you kind of make this carbon, because you're pulling its electrons away. 4 of them are being pulled sort of away. This thing is starting to feel what? Positive. Now, it's not a complete positive, but it's got some positive. It's starting to feel a little positive here.
Slightly positive.
Right. So, it's not a polar molecule, by the way, because both ends of the molecule have the same electron density, but it's not polar. But in the middle, there is some positive. And guess what? Water, who's got a lone pair, it's got 2 lone pairs, can donate this low pair, and it's attracted to that. So these lone pairs are attracted to this positive. So what happens, throwing over here, we have the lone pair of the oxygen, okay, and we have the carbon here. We just made a bond. Now, 2 of these electrons will jump to the oxygen. So this will be 1 bond now. This oxygen has more electrons than it likes. It's going to be negative. This double bond over here, that's what this is. is still here, 2 lone pairs. And then we still have an H bonded here, an H bonded here, and we still have a lone pair here. This becomes a positive. Okay? Now, if you're not following me, carbon still has 4 bonds. 1, 2, 3, 4. Okay? And we've added a pair of electrons here. And now, this H is going to move to this negative. And what we have is a carbon with this same double bonded O. Stay with me for a second. This is going to be to an O bonded to an H. And this is going to be bonded to an OH. And this right here is called carbonic acid. That's what, when they said CO2 or, there it is, H2CO3. So that's H2CO3. I just showed you something called a reaction mechanism that you'll be writing in organic chemistry. Okay? You don't have to do that, it's not part of the course, but you need to know this. You bubble CO2 in water, you're going to make carbonic acid. Now it's this chemical that will donate a proton to lower the what? pH, and make the what? Conjugate, hey, if this is the acid, this must be the what?
Base.
And what's its charge if it gave up a proton?
Negative.
Hey. So CO2 has no H to donate, so it directly is not a Bronsted Lowry acid. So it doesn't fall under, but what did it do? Okay, the carbon in the CO2 was a lone pair acceptor. It was a pair of electron acceptors. So to be a Lewis acid, we say it's an electron pair acceptor. You say, I don't get that. That's odd to me. Wait a minute. Lewis definition is all-encompassing, isn't it? Anything that's an acid must be a Lewis acid. It's the biggest circle. Even acids that are Arrhenius acids are also Lewis acids. What is the bottom line to be an acid? You think about it. Everything we just learned. What's the bottom line? You're dealing with what in the most simplest terms? The H positive. So we talk about the bottom line. This makes our pH drop. It's about the H plus. Now, party people, H plus. When it reacts with water, okay, what's it doing? What does this have? 1.
Hit the roof.
1, 2, 3, 4, 5, 6. Okay, this is H plus. What's happening to make water? What is the H plus doing?
Going to the H.
It's not donating, it's accepting a lone pair. And why would it want a pair? Here's H. H has no electrons, H plus. And when it becomes 2 electrons, it fills its what? Energy level. So on the most simplistic terms, okay, this guy accepts a pair of electrons. And what did the base do on its most simplest terms? It was electron pair donator. What makes nitrogen a nitrogenous base in DNA? What makes nitrogen basic? What did it have? I talked about it. What does it have?
Lone pair.
It's got a lone pair. Things that have lone pairs are bases. Nitrogen is the most famous of them all. Okay? So, Lewis bases are what? Lewis acid electron pair acceptors. CO2 accepts a pair of electrons because the carbon is exposed as a positive. Electrons are pulling away so it can accept the lone pair. And through this mechanism, it winds up making an acid that gives off a proton, a weak acid. Okay? And a Lewis base, well, that was the water acting as a base. It was a lone pair, electron pair, donator. Okay. Moving on to the next page. I won't be doing the entire period, so just stay with me. Okay, what's KQ again? KEQ is that formula that gives me a number that tells me the position of how much reactants and products are when there is no more spontaneity in the forward and the reverse. It's a position where there's no more work being done. It tells me who's favored. KQ by definition, very simply, is the concentration of the products over the concentration of the reactants to their respective coefficients. Again, we'll look at that more later, but we're going to use it. Now, because we're dealing with acids, we'll call it Ka. It's got another name. If I'm dealing with water, we call it K. Right. Now, let's look at these acids right here, party people. All right? Notice these Ks are very what?
Large.
That means who's bigger? The products. If I am an acid that produces tremendous amount of products. In fact, we would say that those in this chart don't really have an equilibrium. They go one way. Their completion. Every single one of these does what? Gives off an H. There's no pushback. There's no reverse. So who are the strong acids? These top 5 in this chart. Why? Because their Kas are so big, you don't even have a number. Why don't I have a number? Well, probably because this concentration of reactants is approaching 0. It's approaching undefined. Is there one of these that didn't let go? Maybe. But if I put a 0 here, it almost becomes undefined. It's going to infinity. Because the reaction goes completely forward. Strong bases completely dissociated. Hey, how did we start our day today? I made 0.1 molar hydrochloric acid. Give me a pH of what? 1. Because I assume that every HCl completely dissociated and the concentration of the H plus was a concentration of the strong acid. That's what last night's homework was about. Now, which are the strong acids right there? Which is the strongest acid listed here? Well, HI is listed higher. Now you say, oh, very large. How is very large bigger than very large? Well, they think HI is a little bit bigger. Now, HI is high. Now, why? Well, let's look at 3 right here. Look at, I'm going to draw group 18 atoms. Fluorine, bromide. That didn't feel right. Fluorine. And iodine. Now, these are my halogens. What happens to the size of the radius as I go down? Because I have what? More shells of electrons, right? We're gonna learn that number is called the N number, but it's okay. Now, when you become negative, as all these guys do, they love to gain 1 electron to become stable. It becomes stable like a noble gas, right? When you gain an electron, you get bigger or smaller? Because now you have more electrons and protons, it pulls away. So these guys are even bigger. Okay, but because they're starting small, the smallest one's still F, the biggest one's iodine. Now think with me for a second. Why would HI dissociate more than the others?
Because it's so large it can't attract.
Because it's so large in a -1, these are all -1, that it doesn't attract this conjugate base very well. Perfect. There's an AP question right there. Explain why HI is the strongest acid. Because this proton, H+, doesn't attract this ion as much. Because, guess what? Coulomb's law, the diameter is so big, you square it, the force of attraction is small. This only hits a small part of the -1. Everything we've learned is still popping up. Okay? By the way, strong acid. Strong acid, strong acid. Can you guess why HF is not a strong acid?
It's so close, and it's hard for the H plus to
Exactly,
break away.
the size is smaller. Also, the electronegativity, the attraction of electrons is also so great with it because of that size. Okay, HF is not on there. Notice where HF is. Look, these guys are very large. Look where HF is. That's a number smaller than 1. Who's favored? The reactant just barely dissociates. And notice the break. We have complete dissociation, almost. And then we have almost no dissociation. There's no in between. Either really good at relieving it or, you get some pushback, which means the reverse. What's your question?
I was gonna say, does fluorine by itself make other compounds or like stuff really good with the bases, since it like steals electrons. So it just-
Absolutely. And that's where the connectivity of redox and acid-base comes into play. This gaining and losing electron kind of deal is part of the interconnectivity of the redox. Okay? So yes, we put it that way. Okay, now, some basics here. Oops, sorry with the pun. If I'm really good as a strong acid, now listen, this is the best explanation, but here, listen to my explanation for this to be a strong acid. Sorry for sitting here and speaking today, but I have to get through this. Why are these strong acids? Ooh, conjugate pairs. What are all these guys? Conjugate, this is what's left over after the acid dissociates. This is a conjugate what? Right. The acid becomes the conjugate base. Party people. What are the strength of these conjugate bases? Now, what do bases do by the Bronsted Lowry definition? It's the one that we kind of stay in. It's the easiest to understand. They accept H pluses. So wait a minute. I'm producing a conjugate base. It accepts H pluses. I should be reforming this acid. But if I'm going just one way, what does it say about the strength of the conjugate bases?
Low.
Right. I'm a strong acid because my conjugate base has no ability to accept the proton back to reform the acid. What must be the case for these weaker acids? There's your vinegar.
They're really good at accepting.
Vinegar dissociates 5% of the time. That means that weak acid produces a strong conjugate base that must be really good at what? Right. Why does water have a Ka that's so small?
Because they react. Because
They just come back together.
Yes! Yes! The reverse is so much better, which is exactly what you just said. So it's the same reasoning here. So as the acids get what? Lower Ka, which means more reactants are being favored, right? They're getting weaker. The amount of dissociations becoming less and less. It must be due to the conjugate base being more spontaneous in the reverse. It has a greater, these guys have what? Greater ability and greater ability to accept the H back, which causes the acid not to dissociate that well. I give off an H, I now am a conjugate base, boom, I grab it back again. If I'm stronger as a conjugate base than I am an acid, I'm going to have a lot of undissociated acid sitting around. And if you look down table K, you'll find something very interesting. Look at this one. Look at the conjugate. Look at water. Its Ka is 1 times 10 negative 14. That must be the what? Conjugate base of water. Okay? So much better to go that way. All right? So, let's do this. Very simple. What's the conjugate base of NO3 negative? Think about this. Think about it. Wait a minute. Conjugate base of this. That means I'm looking for what it becomes as a base. All right? So, no. I want the base of this. So this must be an acid. What acids do? What acids do?
bring the pH down.
Right? So if you look at this, what's the conjugate base of NO3? And of course, there's no way I can write that, so that's a mistake. Because if I'm looking for the conjugate base of NO3, right? I'm looking for the what? The form of it after it acts as an acid. It has no H's to give off, so this is a bad question. All right.
Nothing.
I should have said, what's the conjugate base of HNO3? Okay, so that was a trick question because my worksheet's messed up. So the conjugate base of HNO3, if I'm looking for the conjugate base, I'm looking for what it becomes after it acts as an acid. I want the base of this. So it's an acid. Acids give off H's, so this would be NO3 minus. Sorry to confuse you there. And by the way, look up here. These are all conjugate acids. Where's the acid? Called nitric acid. Its conjugate base? What's left over? Okay, now let's do this. What's the conjugate acid of HPO4 negative 2? Hold on. I want the form of the conjugate. I want its pair when it becomes an acid. Right now it must be a what? A base. What do bases do? Accept. So what will this look like after it accepts and has one more H? H2PO4 -1. The acid will always have one more H than the base. The base will have one less of the acid, right? Because the acids give. So by me saying what's the conjugate acid, I want the form, we're starting with the base. I want the acid of this. This must be a basis. Bases do what? Accept. So this has to be H2PO4. By adding a proton, it's now -1. What is the conjugate? I'm going to make this up. So this is going to be H2PO4 -1. Let me give you this one. What is the conjugate acid of Cl negative? HCl. It's that simple. If it's, I'm looking at the conjugate acid, so I want its form as an acid. Right now it's a base, and of course, the acid of the base will have one more H. I don't know how you want to think about it, but there it is. Okay, so HCl is the conjugate acid. Okay, the form with one more H than the Cl.
Just add it.
Okay,
When you go
however,
to base, add.
okay. Now look at number 6 for a second. Which I'm going to skip 5 for a second. Which is the conjugate base is weaker? SO4 -2 or S -2? Now let's go to the chart. Let's go find SO4. SO4 would be up here. And SO S -2 is below it.
All the way down there.
Yep. Now, which conjugate base is weaker?
SO4 -2.
Right, SO4 -2. Why is it weaker? Because this is a strong, its conjugate what? Its conjugate acid is stronger. Because this is not good at reforming the what?
Conjugate base.
What?
The conjugate acid.
Oh,
Okay?
okay.
Acids get weaker. The Kas get smaller. The conjugate bases are getting what? Stronger. And they're grabbing those H pluses back and reforming the acid to the point where you can barely have any what? Dissociation. Yes?
I would think that the SO4 would be better because oxygen is like really strong.
But you're looking just at oxygen. You've got to consider the ion, the size, what the sulfur does as a group. The chemistry gets complex now. You just can't look at the one oxygen. Yeah, it's got 4 oxygens, but it's surrounded by a sulfur who actually has a positive charge, and it creates, there's all things that come into play here. Okay? Now, last little piece. Draw a representative sample of HF. HF strong or weak?
Weak.
Right, its Ka is less than 1. So I'm going to draw a lot of what? Does that mean I draw all of them?
No.
Dissociated? It's a weak acid. How about HBr?
All
Yeah, it's a strong acid, so complete dissociation you can assume. It's pretty simple stuff there. Okay, one last piece, and we're done today, and the rest of the time you can spend on the order poem. Sorry for talking so much. What the heck is copper H2O? Okay, look at this right here. What the heck is this?
Would it be a hydrate?
Well, no, and it's a good guess. Okay, let's do this.
8.
Watch. If I drop Christmas, let's say I take copper nitrate, copper 2 nitrate. I drop it in water. Just take this last little piece today. It's going to make copper plus 2, and it's going to make 2 nitrates. Right? This is aqueous. Okay? Well, it's solid going to aqueous. Who cares? Now, the point is, in my solution, I have copper plus 2. I know I have nitrates too. Now, because copper is moving across the periodic table, it's transitioning from a very big atom to a small one. It's right in the middle. It's pretty small, comparatively speaking, to the ones over here. And it's got a positive 2 charge, Coulomb's law. It's got a high attraction, high force of attraction. It pulls in the water molecules. It pulls in the water molecules so much that only 6 can fit around it. And it makes something called a complex because it tracks the water so much, it pulls them in to create an actual shape, which is called an octahedral. Okay? It has 6 water molecules, so I'm going to draw them the best that I can. So these water molecules, notice I'm drawing the oxygen end, which is the negative end, is getting pulled in. And there's, why 6, you say? Because sterically 7 can't fit. Only 6 can fit. If you put 7, the electrons of that one water will repel the others and they'll disband it. So only 6 can fit. This is a structure we know. It's called a complex. Is it bonded? Not really. Some people will argue it is, but for the most part we say these are attractive forces. And I have 5, and I'm doing the best I can.
Nature really likes hexagons.
It does. Now, so you notice we write this as copper with 6 water molecules. H2O, 6. We put a bracket around this because copper is still +2. This whole complex is +2. Now, why am I showing you this? Well, this is acidic. This +2 in the middle is doing something. So if I make this bigger, okay, it's +2. And let's draw an oxygen. Let's draw the electrons. We know they're closer to the what? Oxygen side, so here's my H's. Polar. Now what happens is, because of this +2, it's so small and highly charged, it does this. White would be great.
White.
Yeah. It's going to drift these electrons toward the ion. So it's going to make these go even further away. And when that does that,
These become
this
H
proton
pluses.
can what?
Move away.
Slough away. So copper ions dissolved, or any complex, is going to lower your pH because you're going to increase that. So what happens is this will become Cu.
Hydroxide.
Hold on. It'll become this.
Copper.
I'm sorry, I should have wrote this better, but to be copper, this will be H2O, be 5 left, and then there'll be a hydroxide. And what do you think the charge is here?
Positive.
Correct.
One.
So when this goes this way, it donated a proton and is a Bronsted Lowry acid. Or what happened here? Didn't this accept a pair of electrons? Copper plus 2 is a Lewis what? Acid. So go back to reality. What do we have here, party people?
CuH2O5.
I have a bunch of them. Aluminum H2O6 plus 3 is acidic. What else do we have? Iron is acidic. So what's the conjugate base of Cu? I just drew it. What does it look like with one less H? And it would be Cu
H2O5 OH plus 1.
and a hydroxide, and the whole thing is +1. Okay. So, what I want you to do now is take that worksheet, and I want you to do the last one, the last 3. So take the worksheet. I want you to start from this one so I can go over this one. Okay?
Only
Where it says
last
give, well, you're going to do the whole thing. The back will leave blank right now. But this, you do all 3. But I want you to do the last one here. Okay? And I'll pull that up now.
One pen. This is a base. This is an acid. That's an acid.
Oh, this is acid-base chemistry. And we're doing the what? Conjugate acid-base.
Bad.
Okay. This is troubling, isn't it? Wait a minute. Couldn't this guy give off an H?
Yeah.
Couldn't it accept an H?
Yeah.
Same thing for this one. These are called amphoteric. They can act as an acid or a base. So how do I know which one acts as an acid?
Does it not matter?
It does matter.
Oh.
The one who is a better acid will be the acid.
We'll do. So
Yes.
H.
Somewhere you have to look. Go find these chemical species somewhere and look for their Kas.
HPO4 is strong.
What is the Ka?
I mean, no, sorry.
What is the Ka of HSO4, SO3 negative?
1.1 times 10 to the negative 7, which is higher than
1.1 times 10 to the negative 7. And this one is
2.2
2.2 times 10 to the
negative 13. Yeah, I'm a loser for knowing that. Okay, these are Kas. Of course, who's bigger? Why
Yeah.
does that work? Kas are what? Concentration of products over reactants. So if I've got a bigger Ka, I've got more products, which means the what? The acid makes more what? H pluses. This is your acid. Booyah! It is higher Ka. So this must be what? Your base. Now finish it. Donates a what? Proton. So it becomes SO3 negative 2. This guy accepts it. H2PO4 negative
1.
Right. Booyah! Who are my acids?
The HSO3 and the H2PO4.
And on the reverse, if this is a base, this must be the conjugate acid. If this is the acid, here's its conjugate base. How low can you go? Death row, what do I know? Okay, so HSO3 is an acid. Who else is an acid? H2PO4. And if you're confused about this, make sure you put negative 1. If you go in the reverse, this one must be what? Donating a proton to reform the what? Conjugate base that it is. Who are my bases? Who are my bases? HPO4, negative 2. Who are my acids? And then,
negative 2.
now, who are my conjugate pairs, party people? If this is my acid, this must be its
Base.
Conjugate
base. If this is my acid, it's my conjugate base. Notice the base has what? One less proton than its conjugate acid. The rest of the worksheet is for homework. I'll post a key. That's it. Sorry for talking so much, but I had to get through that. Basics. And I will post this, maybe.